Hello students, welcome back to another session where I am planning to complete low temperature refrigeration and cascade systems. So let us complete the theory part in this particular session, and then we will solve the problems on this topic as well as the earlier topics. That may take another 2 sessions, and we need 2 more sessions to complete the evaporators, condensers, compressors, and throttling valves. So these topics are left out in this unit. We will be covering those in another 3 or 4 sessions. So there will be the completion of the unit. So we are completing this unit very soon. So these are the topics we have seen so far. So these are all the topics we have in our second unit. So in today's session, we are going to see low temperature refrigeration system and cascade system. So what is low temperature refrigeration system, and what is the cascade system, and what is its necessity, that we are going to discuss in this topic, students. So low temperature refrigeration system is otherwise called as cryogenics. So cryogenics is a part of the engineering where it deals with low temperatures only. So I will give you its definition and why it is called as low temperature refrigeration system. So introduction to cryogenics, to introduce low temperature refrigeration. The term cryogenic is derived from the Greek word cryos, meaning cold or frost. So in frost condition also we can deal this particular topic. It refers to very low temperature refrigeration applications that includes liquefaction of gases, study of physical phenomena at temperatures approaching absolute zero. So now the liquefaction of gases, that is, the gases are turning out into liquids. So that is the phase change. So that comes under cryogenics. And the study of physical phenomena at the temperature approaching absolute zero. So that also we see here in this low temperature refrigeration system. So we are going to see the definition here. It is nothing but the refrigeration temperatures between minus 100 degrees Celsius to minus 273 degrees Celsius. So that is absolute zero are considered low temperatures. So minus 273 degree Celsius is also known as absolute zero. So are considered as low temperatures. So history of low temperature refrigeration. Early developments in low temperature refrigeration focused on solidifying carbon dioxide and liquefying gases. So this is the earlier usage, and where the low temperature refrigeration came into picture. And then oxygen liquefaction. So it is actually came into picture in the year 1877 by uh, Cailletet and Pictet. So this is Pictet. So Cailletet and Pictet, these are the two scientists who achieved this oxygen liquefaction. Hydrogen liquefaction, it is accomplished in the year 1898 by Dever using Joule-Thomson expansion. And then boiling points of gases. So liquid oxygen, it is 90.2 degree Kelvin, and that is minus 182.8 degrees Celsius. Liquid hydrogen is 20.4 degree Kelvin, that is minus 252.6 degree Celsius. Helium liquefaction achieved in the year 1908 by Kamerlingh Ons, reaching 1.1 Kelvin. So this is 1.1 Kelvin. So that is minus 271.9 degree Celsius. By 1928, further improvements reduced the temperature to zero point 0.7 degree Kelvin. So still again we are reducing the temperature here. In 1933, Gadik and Debe introduced adiabatic demagnetization using the paramagnetic salts reaching temperatures as low as 0.001 degree kelvins. So even he has gone to 0.001 degree kelvin also. So this is done in the year 1933 by Gadik and Debe. So limitations of vapor compression refrigeration for low temperatures. So vapor compression system we have seen all along in this unit. Now the limitations, why the low temperatures it is not much suitable, that we are discussing here, and what is the solution that we are going to discuss here. So in earlier cases, in earlier session, I have given you the necessity of cascade system and why we go for cascade system. I have explained in our earlier session, and we will see the limitations of vapor compression refrigeration for low temperatures here. The vapor compression refrigeration systems can typically achieve an evaporator temperature of minus 40 degree Celsius. Further cooling is limited by the refrigerant solidification temperature. So challenges of vapor compression system for low temperatures are the refrigerant solidification, and refrigerants must have freezing points lower than the target temperature. The refrigerants like R13, R717, that is ammonia, R744, so that is CO2, carbon dioxide, R764, that is SO2, sulfur dioxide, are used for lower temperature applications. So these are more suitable refrigerants for low temperature applications. Low pressure in the evaporator below atmospheric pressure is required, making the suction volume large when high boiling point refrigerants are used. So when high boiling point refrigerants are used, so that yields to below atmospheric pressures are required, and this is the low pressure in evaporator. High pressure in the condenser. High pressure in the condenser, low boiling temperature refrigerants results in high pressures in the condenser. Low coefficient of performance, that is COP. This is due to very high pressure ratios. So that is condenser pressure to evaporator pressure. Mechanical difficulties at very low temperatures, so that is operational challenges arise due to extreme conditions. So even operational challenges are arising due to high extreme conditions. And freezing temperature of common refrigerants. So I am giving you a small table here. This is the freezing temperatures in terms of Celsius. So refrigerant, for each refrigerant there are freezing temperatures. For R11 it is minus 111 degrees Celsius. For R12 it is minus 157.5 degrees Celsius. For R21 it is minus 135 degrees Celsius. For R22 it is 96.6 degrees Celsius. For R40 it is 97.5 degrees Celsius. For R113 it is minus 35, and for R717 it is, that is ammonia, that is 77.8, and for R744 that is minus 56.7. For R764 for sulfur dioxide it is 75.6. So these are the freezing temperatures of common refrigerants. So then to to provide solutions. These are the limitations. To overcome those limitations, we have multi-stage compression systems. They are also called as cascaded systems. Cascaded systems. These are used to overcome the limitations of single stage vapor compression systems. And these are the examples. Two stage system using R12, it operates at minus 60 degrees Celsius. Three stage system, it achieves minus 68 degrees Celsius. So now two stage, it is up to minus 60 degrees Celsius we can operate, and for three stage still we are going lower, that is minus 68 degrees Celsius. So then the multi-stage systems, these are also called as cascaded systems. Now we will move to cascaded systems and see the real system, the how the cascaded manner of condensers are placed. So that we are going to see here. The cascade refrigeration system is used when extremely low temperatures below minus 100 degrees Celsius are needed. So here extreme low temperatures, that is minus 100 degrees Celsius. So in this case the cascaded refrigeration system is highly applicable. So it consists of multiple refrigeration cycles operating at different temperature levels with each cycle using different refrigerant. So here, as I said in earlier session, we can apply different refrigerants for each stage. We can apply one refrigerant. So no need to limit ourselves to single refrigerant. We can add the number of refrigerants as per our number of stages. So why the cascaded systems? Single stage or multi-stage refrigeration systems face challenges at very low temperatures due to high compressor pressure ratios leads to inefficiency and mechanical failure, limited refrigerant effectiveness. Some refrigerants cannot operate at such low temperatures effectively. So for that examples are R13. R13 can be used below minus 100 degrees Celsius, but needs cascading of avoiding extremely high condenser pressure, and that is extremely, it should be avoided. High condenser pressure should be avoided, and the critical temperatures of R13 are 28.8 degrees Celsius. If used alone, the system would experience extreme pressure issues. So that is another disadvantage here. So critical temperature is 28.8. If used alone, the system would experience the extreme pressure issues. So pressure may shoot up, that should be reduced here. So working principle of cascaded refrigeration. So multiple refrigerants with progressively lower boiling points are used. The cascade system consists of separate refrigeration cycles. So each stage will have each refrigeration cycle, each operating with its own refrigerant. Heat is transferred through a cascade heat exchanger where the condenser of low temperature cycle acts as the evaporator of the high temperature cycle. So here that is the cascaded advantage, or we can say the cascaded arrangement. So the condenser of low temperature cycle, that is LT cycle. So we are going to call low temperature cycle as LT cycle, acts as the evaporator of the high temperature cycle. For high temperature cycle, it acts as evaporator. This allows efficient cooling at extremely low temperatures. So example of a two-stage cascaded system is first stage high temperature cycle. So first stage is considered as HT cycle and uses refrigerant like R22 or R717 ammonia, removes heat from the second stage refrigerant. So now the first stage removes the heat from second stage refrigerant. So that is second stage refrigerant is different. And second stage, low temperature cycle, so that is LT cycle, uses a refrigerant like R13, R23, which operates at ultra low temperatures, absorbs the heat from the load and transfers it to the first stage. So that is the absorbs the heat from the load and transfers it to the first stage. So that is the second stage, and we have these two stages in two stage cascade system. So this is the two-stage cascaded system. As I said earlier, so this is the low temperature cascade system. So this is evaporator and this is the condenser. So this is the cascaded condenser and low temperature cascade compressor, and this is high temperature cascade compressor. So we have two stages, LT stage and HT stage, and here this acts as cascaded condenser. So two refrigeration systems are cascaded like this using the cascaded condenser. So now here this is the first stage and this is the second stage. So in this first stage, this condenser acts like a condenser in first stage, but in second stage, in high temperature cascaded system, this condenser acts as evaporator. Instead of condenser, it acts as a evaporator where condenser is provided here. A separate condenser is provided for high temperature side, that is cascade system. So this is the arrangement, and the mass of refrigerant M1 in LTE side and M2 in the case of HT side. So this is the simple arrangement. So for each stage there is a separate thermodynamic cycle. So thermodynamic cycle is an offset of each other. So there will be offset distance. I will show you that. So in the diagram shows the two-stage cascade system. It consists of low temperature cycle, LT cycle, and uses refrigerant with a very low boiling point. Evaporator absorbs heat from the refrigeration load. Compressor compresses the refrigerant to a high temperature. The refrigerant rejects heat into the cascade condenser. So cascade condenser acts as heat exchanger between LT and HT cycles and absorbs heat from the LT cycle and transfers it to the HT cycle. So now it absorbs heat from the LT cycle, low temperature stage, and it releases to the HT cycle. High temperature cycle, HT cycle, uses a refrigerant with a high boiling point. This cascade condenser acts as an evaporator for HT cycle, and compressor in the HT cycle raises the refrigerant pressure. The, the heat is rejected to the external environment via the condenser. So the condenser in the HT stage that releases the heat to the environment. So this is how the both stages work. And if you see its key points, two-stage cascaded system key points, the cascade condenser ensures efficient heat transfer between the two cycles, and refrigerant selection is very crucial. HT cycle refrigerants are normally R22, R12, R717, NH3. LT cycle refrigerants are normally R13, R503, R23. Thermodynamic cycle, if you see, there is the same thermodynamic cycle like our vapor compression refrigeration system, but here the difference due to the cascaded condenser. So now this is the pressure enthalpy chart, and here it starts and it goes up to 6. In between we have stages. So this is the first one, and this is the notch, and it is for HT and this is for LT, and this is enthalpy on x-axis, it is enthalpy, and here you can see the offset. So this is the offset from 6 to 2, it is offset, and this is happening in low temperature compression, and this is low temperature compression. So from 1 to 2 is low temperature compression. So here from 1 to 6 it is high temperature compression, and this is the high temperature condensation, and this is high temperature expansion. Whereas here the 2 to 3 is cascaded condensation, and from 5 to here this is 5 to 8 this is cascaded evaporation. So this is cascaded evaporation, and 3 to 4 it is low temperature expansion, low temperature expansion, and this is the two stage diagram. So this is dotted line is low LT, and this is solid line is HT. So these are the two offset cycles you have to show here. Similarly here this is LT and this is HT. So two offset. So this is the distance between these two, and that offset is very having very high significance, and two cycles you have to draw with equal that is offset distance. So this is the thermodynamic cycle for two stage compression. So pH diagram graphically represents the thermodynamic processes of the refrigeration system. pH diagram on TS we have seen in earlier slide. Evaporation in LT cycle, that is from 1 to 2, the refrigerant absorbs the heat from the cooling load at the pressure, at low pressure. So the compression is taking place from 2 to 3, the low pressure vapor is compressed to high pressure. So heat rejection in cascade condenser, so that is 3 to 4, the refrigerant releases heat to the high that is high temperature cycle and condenses. So the expansion is taking place between 4 and 1. So the refrigerant expands back to low pressure. So this is the pH diagram, and evaporation in HT, so that continues from 5 to 6. The refrigerant in the HT cycle absorbs the heat from the cascade condenser, and compression in HT cycle. So now again HT cycle is taking place. So that is 6 to 7. The high pressure vapor is compressed further. Heat rejection in HT cycle, that is 7 to 8. The refrigerant releases heat to the external environment via the condenser. So here 7 to 8 is a heat rejection process in the thermodynamic cycle, and then we have expansion in HT cycle, that is 8 to 5. So 8 to 5 I have shown you the same. 8 to 5 is expansion in HT cycle. The refrigerant expands back to low pressure. So temperature entropy diagram of two stage cascade diagram, and this TS diagram shows how temperature and entropy change during the refrigeration cycle, and the LT cycle operates at low temperature range, the HT cycle operates at a high temperature range. The cascade condenser acts as an intermediate heat exchanger, and key insights if you see here, the low temperature difference improves efficiency, and minimizing entropy generation leads to better COP. So we have seen a two-stage system, cascade system, whereas we go for multi-stage cascade system here. More than two refrigeration stages are used when ultra-low temperatures are needed. So still more low temperatures if we require, then we have to increase the number of stages. Three-stage cascade system introduce an intermediate refrigerant to improve performance. Three refrigeration cycles are connected via two cascade condensers. So now in earlier case we had only one cascaded condenser, that is condenser of low stage and condenser of high temperature stage. So both are both acts as a heat exchanger there. Similarly here we are going to use two cascade condensers. Refrigerants used in each stage, so methane, that is in first stage, ethylene, that is in second stage, C2H4, and ammonia, that is NH3, that is used in third stage. So multi-stage cascade system diagram, we are extending one more stage. So that is only difference between the two-stage compression and two-stage cascade system and three-stage cascade system here. And the diagram is like this. So this is the low temperature cascade system, and this is intermediate temperature cascade system, and this is high temperature cascade system, and we have two cascade condensers. So this is the first cascade condenser, and this is the second cascade condenser. And now the condenser should be provided, a separate condenser should be provided at a high temperature cascade system. And now these two acts like a heat exchangers between stages. So this is a simple diagram for multi-stage cascade system. So multi-stage cascade system, say similar to earlier one, we have three peaks and we have three stages. So the dotted line, it is intermediate stage, and this solid line 1, 2, 3, 4 is the first stage, low temperature stage, and 9, 10, 11, 12 is the high temperature stage. Similarly here we have three stages in TS diagram as well. So A, B, C represents three stages. So low temperature stage, B is intermediate temperature stage, and C is the high temperature stage. And these three you have to remember, students. So we go up to three stages. No need to go to fourth stage. So that becomes a little complicated, and we stop with three stages itself. And if you see the difference in low temperature cascade condenser temperature and high temperature cascade evaporator temperature is called overlap. So temperature overlap. So the difference in low temperature cascade condenser temperature, cascade condenser temperature, and high temperature cascade evaporator temperature is called the temperature overlap. So between these two stages we have this temperature overlap. This is necessary for heat transfer. If these temperatures are equal, then it is known as intermediate temperature. So intermediate temperature is when the heat transfer, so when the heat transfer is taking place, if these temperatures are equal, then intermediate temperature rises. So that is the overlap. It is a 2 mark question. Intermediate temperature, it is also a 2 mark question. So multi-stage cascade system, three-stage cascade system consists of low temperature cascade system. It uses methane as a refrigerant, and evaporator absorbs heat from the refrigeration load. The temperature is compressed and released. Heat releases heat in the intermediate cascade condenser. So intermediate temperature cascade system, here it uses ethylene. So we have three stages. We are using three different refrigerants. So that is the advantage in this cascade system. And it uses intermediate temperature cascade system uses ethylene as the refrigerant. And cascade condenser serves as the condenser of the low LT cycle and the evaporator of the intermediate temperature cycle. So heat is transferred to the high temperature cascade system, and the high temperature cascade system is, it uses NH3 ammonia as the refrigerant. The heat from the intermediate temperature system is absorbed and released into into the external environment through the stage 3. So high temperature cascade system. So here the heat from the intermediate temperature system is absorbed and released into the external environment. So that is the uh, outside the system, it releases. So pressure enthalpy diagram of three-stage cascade system and pH diagram shows the thermodynamic cycle for each refrigerant. So three refrigerants are used at three different temperature levels. Each cascade condenser ensures efficient heat transfer between adjacent cycles. Temperature enthalpy diagram, entropy diagram of three-stage cascade system. So that gives the TS diagram represent the variation of temperature with entropy in three-stage cycle. And the key insights from this is each stage has its own temperature range. The cascade condensers act as thermal bridges between stages. Ammonia NH3 is also used in the high temperature cascade system for the manufacture of solid carbon dioxide, that is dry ice. So solid carbon dioxide is nothing but dry ice. So it is very much used there. So advantages of cascade refrigeration system is efficient operation at extremely low temperatures, so that is minus 100 degree Celsius, reduces compressor pressure ratios, improving reliability and performance, allows optimal refrigerant selection for different temperature ranges, enhances energy efficiency compared to a single stage system, and minimizes mechanical stress on compressors, leading to longer system life, and prevents mixing of lubricating oil. Unlike multi-stage compression systems, a cascade system prevents the compressor oil from wandering between different compressors. It ensures better refrigeration selection where each stage can use an optimal refrigerant suited to its temperature range. So depending on the temperature range, we have flexibility to use different refrigerants. So cascade refrigeration is essential in ultra low temperature applications like cryogenics, scientific research, and specialized industrial processes. It allows efficient and reliable cooling while overcoming the limitations of traditional refrigeration methods. So this is another efficient and reliable cooling. It provides a more reliable cooling system. Next, the coefficient of performance of a two-stage cascade system. It is the schematic and pH diagrams of two-stage cascade system is already we have discussed it, and from that the Q tons of refrigeration is the load on the low temperature cascade system when the mass of refrigerant flowing through the low temperature cascade system. So that is given here like M1 equal to 210 cube divided by H1 minus H4 kg per minute. So the mass of refrigerant M2 required in the high temperature cascade system in order to liquefy the refrigerant of the low temperature cascade system in the cascade condenser may be obtained by balancing the heat of both the systems. In other words, the heat absorbed is the high temperature in the high temperature cascade system must be equal to the heat rejected in the low temperature cascade system. So this is the obvious process. The heat absorbed in the high temperature cascade system must be equal to heat rejected in the low temperature cascade system. So mathematically, if we balance this, M2 H5 minus H6 equal to M1 into H2 minus H3, and M2 can be computed like this. That is M1 divided by M1 H2 minus H3 divided by H5 minus H6, that is equal to M1 H2 minus H4 divided by H5 minus H6 kilojoules per minute. So then it is H3 equal to H4. We know that the total work done by the system W equal to M1 H2 minus H1 plus WH6 minus H5 kilojoules per minute. So, and refrigeration effect is RE210Q kilojoules per kg, and the coefficient of performance COP of the system COP RE divided by W equal to 210Q divided by M1 H2 minus H1 M2 H6 minus H5. So, this is the coefficient of performance, and the power required to drive the system is P equal to m1h2 minus h1 plus m2h6 minus h5 divided by 60 into by 60, that is in terms of kilowatt. So coefficient of performance of a two-stage cascade system. If the coefficient of performance of low temperature side, that is LT side, and high temperature HT side of a cascade system in terms of evaporator, condenser, intermediate and overlap temperatures assuming reversible Carnot cycles may be determined as below, and let TEL and TCL, that is evaporator and condenser temperatures for low temperature cascade system, and TE is evaporator at low temperature and TC is condenser temperature at low temperature. So TEH and TCH, evaporator and condenser pressures temperatures for the high temperature cascade system. The coefficient of performance of the low temperature cascade system can be now COP of LT equal to TEL divided by TECL minus TEL. So that is at low level. So evaporator temperature divided by condenser temperature minus evaporator temperature. So on coefficient of performance of high temperature cascade system, it is same as LT. So TEH divided by TCH minus TEH. So here the TE it is in terms of a high temperature cycle. In a high temperature cycle, we have evaporator temperature divided by condenser temperature minus evaporator temperature. So when the low temperature cascade condenser temperature is equal to high temperature cascade evaporator temperature, it is then known as intermediate temperature. So that is Ti. So then we can rewrite like this: TCL equal to TEH equal to Ti, and we can rewrite that. So thus the above expression of COP in terms of intermediate temperature T1 may be written as, so COP of LT equal to in terms of TEL divided by TI minus TEL, intermediate temperature minus TEL. So and the COP of HT equal to TL, so Ti divided by TCL minus Ti. So Ti is intermediate temperature. So intermediate temperature is a very important temperature here for it will be very useful in while solving the problems that we are going to see in our next session, students. And we stop here cascade system, and we have two more topics, two more sessions. We need two more sessions to cover different types of condensers, compressors, evaporators and expansion valves, so that we will take up in coming two more sessions. So these are the books. As usual, you can refer this, but R.S. Kurmi gives a very simple explanation for this topic. So I prefer you to refer R.S. Kurmi book. I will give you the important topics from R.S. Kurmi and other books. So you can prepare for your FAT 1. So FAT 1 is from 20th onwards. So it falls on 20th and 21st, and we will discuss when we are going to have our FAT 1. So 21st of March. So either date that depending on your workload at TVS industry, depending on that we will fix the date and we will have the test, students. And then we have references. All these references are you can refer, and these are the e-resources, and you can refer any of this, no problem. But I prefer R.S. Kurmi. R.S. Kurmi gives in a very simple manner, you can easily understand. You can also refer CP Arora, or you can refer Rajput. So any of these books are fine, but my suggestion is please go with Kurmi for these topics. In earlier topics, I preferred CP Arora. So same way you can also follow the books. Thank you, students. We stop here and we will meet again in next session. Thank you. Thank you, students.